If a graph of a function isn't available, we can also estimate limits of functions numerically by plugging in values. This is essentially what we were doing when we estimated instantaneous rates of change by calculating average rates of change. We plugged in values of h to calculate the average rate of change and then saw what happened to the average rate of change as h got closer and closer to 0. Let's look at a few examples of estimating limits numerically. To estimate each of these limits, I'm just going to plug in values of x that are closer and closer to the value that x is supposed to approach, making sure to approach from both sides. Starting with the limit as x approaches 2 of x minus 2 over x squared minus 4. For this limit, x needs to approach 2, so I'll create a table of x values that I'm going to plug in, and then use a calculator to evaluate the function x minus 2 over x squared minus 4 at each x value. Notice that I'm not trying to plug in 2 directly. If I did, I'd get 2 minus 2 over 2 squared minus 4, so 0 over 0. And that's indeterminate. I can't tell you what the limit is just by looking at that expression because 0 divided by 0 could be anything. Limits are about what happens as we approach the value anyway, so we don't actually care what specifically happens at x equals 2. Plugging each of the x values from my table into my calculator, I get the following numbers. 0.256 when x is 1.9, then 0.2506 for 1.99, and 0.25006 for 1.999, and then approaching from the other side, 0.2439 when x equals 2.1, 0.2494 when x equals 2.01, and 0.2499 when x equals 2.001. It certainly seems like the values are getting closer and closer to 0.25 as x approaches 2 from both sides. Soon we will learn how to evaluate this limit directly instead of estimating it, and then we will be able to confirm that the limit is in fact 0.25. The limit as x approaches 0 of sine of x over x. I'll follow the same process for this limit, but now I need x values that are closer and closer to 0 from both sides. I need to make sure my calculator is in radian mode here. Two important things to remember. First, angles without degree symbols are always assumed to be in radians. And we always do calculus in radians. Later on, when we learn the derivatives of the trig functions, the formulas we learn will only be true if the angles are in radians, not degrees. Using my calculator to fill in the table, I get when x is negative 0.1, sine of x over x is 0.998. That is the same value I get when x equals 0.1. When x is negative 0.01, I get 0.9998, which again is the same value I get for 0.01. And when x is negative 0.001, I get 0.9999998, which is the same value that I get when x is positive 0.001. What does it look like the values are approaching here? As x gets closer to 0, it seems like we're getting closer and closer to 1. This limit is important for proving what the derivative of the sine function is later on in the course, but it requires geometry to prove. Notice again that directly plugging in 0 for x does not work because the sine of 0 is 0, so we end up with 0 over 0 again. The limit as x approaches 0 of the square root of x squared plus 9 minus 3 all over x squared. For this example, I want to illustrate what can go wrong when numerically estimating limits. Let's do the same process we've been doing, but use x values that are really, really close to 0. Notice that all the x's in the function are squared, so this is an even function, which means that there's no point in plugging in the positive and negative values separately because they'll always give the same answer. When I plug in positive or negative 0.1, I get about 0.1666. Then when I plug in positive or negative 0.01, I get 0.166662. And then doing the same thing with plus or minus 0.001, I get 0.16667. And then I plug in 0.0001, and I get 0.1667. It's a little weird, but maybe okay. But then when I plug in 0.00001, I get 0. What happened? The values seemed like they were close to 1/6, which is 1.66666 forever. But then suddenly we get 0? The moral of the story is that your calculator cannot be trusted. The limit is 1/6. But when x gets too close to 0, the calculator no longer has the precision to distinguish between the square root of x squared plus 9 and 3. So as far as it's concerned, the numerator is 0. Now, different calculators will have different amounts of memory, so a powerful computer could let x get much closer to 0 before running into this problem. But at some point, every computer is going to have this issue. This is why it's so important to be able to evaluate limits without relying on just plugging values in. The limit as x approaches 0 of sine of pi over x. This last example is a little different because we don't get 0 over 0 when we plug in our x value. Instead, we get the sine of pi over 0, which is definitely undefined. But since it doesn't matter what happens at 0, only as we approach 0, this isn't really enough to say definitively that the limit doesn't exist. Instead, let's see what happens when we try plugging in some values. I want you to pause the video, pick some values close to 0 on either side, and plug them in and see what you get. Press play when you're ready. Did you pick similar values to what I did? Did you get the same results? What does it look like the limit is? It's very tempting to say that the limit is 0, because after all, every value we got as we got closer and closer to 0 was 0. But that's wrong. Your calculator is doing everything correctly, but we as humans are naturally going to choose numbers of a specific type. We are trained by our number system to be drawn towards powers of 10. But when we plug in a number of the form 1 over 10 to the n, which is the same as 10 to the negative n, we're going to get sine of pi over 10 to the negative n, which is the sine of 10 to the n times pi. And the sine of any integer multiple of pi is always going to equal 0. To see what's really happening with this limit, we should look at the graph of the function. From the graph, we can see that the function continues to oscillate between -1 and 1, no matter how close to x equals 0 we get. Zooming in doesn't help. The oscillations just get faster and faster. There is no way to get close enough to x equals 0 that the y values are suddenly getting closer to one particular value. Because of this behavior, we say that the limit does not exist. So not only can your calculator not be trusted, but you can't be trusted either. Our next goal will be to systematically evaluate limits using algebra so that we no longer have to try to estimate them.